So let's do this next bit. So we have power. Power is energy done in a given time or work done in a given time. I think I told you, maybe it was in another class, my brother commented about how physicists tend to like energy and engineers tend to like power. And it was actually, there was a ring of truth to that, because I can remember going through kinematics and thinking that's physics, and then getting to energy and realizing, man, I could have done an awful lot of those questions from kinematics if I just looked at energy. So energy is a really useful methodology. If you can think of how to do things using energy, it's often a very nice way of answering a physical question. And of course, energy tells you how much energy you need to do something. But from a practical point of view, when you get asked, can you build a pyramid, then the physicist always answers yes, because, yeah, it's just so much energy. It might take me 7 generations, but it's so much energy. Whereas in the practical world, what you want to know is, can you build a pyramid this week? That's power. If you have not enough energy per second, you cannot achieve that task. So engineers have to think in terms of power, because they need to complete jobs in a reasonable time, whereas physicists can say it's possible, you know. So energy is useful, but it's got its limitations, and so power is really valuable. So we talk about instantaneous power, which is just P, capital P, and we talk about average power, which is P with a little bar on top. And really, power equals work, there's a symbol missing there, over the change in time. It's the duration. And so I say a student uses a pulley system to lift a 9-kilogram bag of cement 5 meters vertically. And the job takes 12 seconds. There's my clock. And it goes, what power is required? So the average power equals the work done over the time taken, which equals the force times the distance over the time taken. And although my pulling force is down here, it's over a pulley, which means that that's also the force. So I say my power is equal to, let's have a look. What work am I doing? Well, my work is, I can use MGH. I can say work is equal to my change in my gravitational potential energy. So I can say this is equal to I can say work over time. I'm going to change my tack is equal to my MGH over delta T. So power is equal to my mass, which is, well, if this is 90 down, well, it's going to be 9 times 10 times 5 over the time taken, which is 12, which is 9 5s are 45, 450 over 12. So my power equals what, 30? 37.5 watts.
Instead of writing MGH, could you have just replaced the F with 90?
Yes, that's why sometimes you kind of like you do it different ways at different times. The force, this is the force, and the force times that distance is equal to 90, because the downwards force of 90 is equal to the upwards force of 90, assuming a constant speed. So, yeah.
Watts is the typical measurement for power.
And it's steadily. Sorry, yeah.
Watts is the typical measurement.
Oh, so watts is the SI unit of power. If you're working in kilograms, meters per second squared, you are in watts. Yeah. Electric motor is used to steadily lift a 700 kilogram elevator, 120 meters vertically. The job takes 1.5 minutes. What power does the electric motor dissipate? Can you do that for me, please?
What's the components of watts?
I'm sorry?
What's the components of watts?
What do you mean by components?
Like kilograms, like half forces.
Well, what's the equation for power?
Work over change in time.
What's the units for work?
Joules.
And what's the change in time?
Okay, so it's joules per
Yeah, always look at the
joules per
equation
second.
and you can work out the units. Yeah. Okay, so let's have a look at this. Electric motor. There's my motor. Motor.
Oh,
700. 120. My clock says 80 minutes, 80 seconds.
8 seconds?
Yes, minutes.
1.5 minutes.
Oh, 90. Yeah, 90 seconds. Yeah, 90 seconds. So then I say my power is equal to my work done over the time interval, which equals, let's do it the other way, force times distance over the time interval. So this power is equal to, this is going to be, well, if this is 700 kilograms, that's 7,000 newtons. That would be 7,000 newtons times 120 over 90. So power is equal to 7,000 times 120 divided by 90 is equal to C.
Although it's a long time.
3.
Why don't we divide by the gravity? I mean, times the gravity? Or no?
Why do we multiply what by the gravity?
Oh, because we have the weight, right? It's
Yep.
not
So.
weight.
And there shouldn't be a decimal.
Last question, we did 9 times 10.
Because I used the mass, and this time I'm using the force.
Use the force.
So how did I get the force? I said if the mass is that, I multiply it by g. So recognize MGH is equivalent to the force times the distance for things that are going vertically.
Alright, but the answer is 9,000.
Yeah.
Okay.
Yeah.
Wait, and your options are 930.
No, this is 9,333.
It says 9. Now it says 900.
So it's just a typo?
No, I made a mistake. I probably used the mass rather than the force.
Use 700.
I messed up. Yeah, I messed up. I cannot tell a lie. I messed up. Instantaneous power. So this is a little bit of an interesting thing. It's a little bit odd. You wouldn't think of it. So if power equals the work done in a given time, then in any instant is the little bit of work done divided by the little bit of time. And the little bit of work is F dotted with ds over time. And ds by dt is distance divided by time, which is v. So I can do F dot v. That's not obvious. It's not obvious that the power at any instant is simply the force multiplied by the vector force multiplied by the vector velocity in a dot product. That's like the most amazing thing. So a spaceship fires its thrusters at t equals 1.25 seconds. The thrusters have a force of 4 newtons, and the spaceship moves with a velocity of 6 meters per second. What power is dissipated? So I would say P, not P with a bar over the top, but instantaneous P is equal to F dotted with V, which equals F times V times the cosine of the angle between.
What? Cosine?
It's a dot product. Cosine, yeah? It's the component of the force with the velocity, or the component of the velocity with the force. Agreed? We all agree on that? So then P is equal to, oh, did I draw a diagram? So then I have no idea really what I'm talking about. So we have our spaceship, and it's equal to the thrusters. So my thrusters are going to make me go forward. It's going to be 4 newtons. And with a velocity, I've been given no directional information. So it's fair to assume it's in a straight line. So that would be 4 times 6 times the cosine of 0. So P is equal to 24. What's the unit's going to be? Watts. Now with dot products, I can mess with you with a dot product. So here's a messing with you with a dot product. Can you do this one for me, please? Any questions on the other one? No? Do this one, please. Agreed?
Yes.
So dot products come up all the time. And eventually we'll do cross products. Have we done cross products yet? We've not done talk yet, have we? They come up all the time. So, just a word to the wise. When I've got a dot product, I've got 3 choices. I can ask you a question where you need to use the magnitude of the force times the magnitude of the velocity times the cosine of the angle between. That's the way we did the first question.
Was the angle between the first question 0?
Yes, it was 0. And another alternative is I give you ijk for the force. I give you ijk for the velocity. And then you do the dot product. There is a third way. And the third way is I give you an ijk for one of them, say the force. And then I tell you the magnitude and the direction of the velocity. So I might turn around and say, in this question, I might turn around and say, well, there's the thrusters, but the velocity is 9 meters per second along the positive y-axis. So I'm using words with a magnitude. And then you got 2 technical choices. You can either try to get the magnitude for the force and the angle between, or you try to make everything into ijk. You've either got to make everything ijk, or you've got to make everything magnitudes with an angle. And I would recommend to you that it's a lot easier to say, well, that would be 0I plus 9J plus 0K meters per second. So just watch out for that, you know. Cross dot by dot, IJK by IJK, magnitude, magnitude, and angle. But I can give you a mixture of the two, and you've got to figure out what to do. Last little thing. My old friend, Mr. Fan, taught me how to do the factor label technique, and I taught you that in Physics 1. So this should be no problem. Converting. So basically, 1 watt equals so many joules a second. 1 horsepower is that. I just want to end here. I can leave you to do this. Horsepower. A horse is not, if you were to measure the power of a horse, it would not be this value. And this comes down to historical. There were two engineers. The business guy was Matthew Boulton. They'd made steam engines, and they wanted to sell the steam engines to factory owners. And the factory owners, this was new technology. This was like people didn't know what steam could do. But people would run factories either using water wheels or using beasts of burden. And all the rich people had horses. So, fellas, please. So all the rich people had horses. And so people were familiar with the power of a horse. The problem is that half the people have a horse which is more powerful than average, and half the people have a horse which is less powerful than average. That's the nature of the average. And so if you say this is the horsepower of a horse, half the people will think you underestimated it, and half the people will think you overestimated it, which means that half the people are going to be really ticked off. So what they did was they deliberately overestimated what a horse can do. And so they sold a 5 horsepower steam engine, and when the people put it in their factories, it would replace 7 or even 8 horses. And so they said, man, this guy Bolton's an idiot. He just sold me this steam engine, and he said it's 5 horsepower, but I'm replacing 8 horsepowers. So how long do you think it's going to last before he catches on? So buy another one real quick before he realizes he's giving the farm away. And Bolton knew exactly what he was doing, and he didn't care. He just wanted to sell you an engine. Psychology. If you buy a car, and I buy a car, and we buy the same car from the same salesman, and you pay $200 less than me, I'm going to feel cheated. Even though that's probably 1% of the price of a car. We have this sense of fairness. We want this sense of having a good deal. And so Bolton deliberately misrepresented what a horse can do so customers would be happy, which is business overruling. No, it's not. It's just the way it is. It's like, so that number's not right, but you don't need to know it, but know how to use it if I give you it. Okay? I'll see you guys next time. By the way, please, for next time, I really am having to shout over people's voices, so please just stop the conversation. Okay.
What if we're conversing about the issue?
I discussed that before and said, if you have a question, put your hand up. If you're discussing physics, you're still disturbing people around you. We talked about that at the beginning of the school year. It's like, I'm sorry, but when I'm talking, I need quiet. Okay.